Imagine standing at the edge of a vast windswept desert. The grains of sand beneath your feet represent moments, each one a fragment of time, countless, immeasurable, and slipping through your fingers as you try to grasp them. Yet, just as the desert's expanse seems eternal, so too does time stretch endlessly before and behind us. A mysterious current we are forever bound to follow. What is this invisible force that governs every heartbeat, every sunrise, every thought? Is time a tangible thread woven into the fabric of the universe, or is it merely an illusion crafted by our minds to make sense of existence? From the earliest civilizations to the most advanced scientific theories of today, time has been a source of endless fascination and profound mystery. Ancient philosophers pondered its nature, poets wrote about its fleeting essence, and physicists dedicated lifetimes to unraveling its secrets. Time is the silent witness to every story ever told, the framework within which the universe unfolds, and the measure of every life lived. Yet, despite its omnipresence, it remains one of the greatest enigmas of human existence. We perceive time as a steady, unyielding river, flowing in one direction, carrying us from the past, through the present, and into the future. This forward march feels immutable, an inevitable progression we cannot pause, reverse, or step outside of. But is this truly the nature of time? Or is it simply how our limited minds interpret an incomprehensible dimension of the cosmos? What if time, as we experience it, is not as rigid as it seems? What if it could be bent, stretched, or even traveled through like a road on a map? These questions take us to the cutting edge of scientific thought. Over a century ago, Albert Einstein shattered our classical understanding of time, revealing it as an inseparable part of the cosmos, intricately linked to space. His revolutionary theories painted a picture of time not as a constant, but as a dynamic, malleable dimension. Time, Einstein showed us, is relative. It can slow down or speed up, depending on how fast you move or how close you are to a massive object. These concepts were not just theoretical musings, but have been proven through experiments and practical applications. For instance, the GPS satellites we rely on daily for navigation must account for time running differently in orbit than on Earth's surface. Einstein's discoveries marked the beginning of a new era in our understanding of time, one that challenged everything we thought we knew. If time can stretch and compress, could it loop? Could we traverse its currents, journeying to the past or future like explorers on a cosmic odyssey? These ideas, once confined to the realm of science fiction, now teeter on the edge of possibility, tantalizing us with their implications. But with the allure of time travel come paradoxes that boggle the mind. Could altering the past erase the present? Could the future influence the past? The infamous grandfather paradox posits a scenario where traveling to the past and changing a critical event, such as preventing your grandfather from meeting your grandmother, would prevent your existence, creating a logical inconsistency. To resolve such dilemmas, physicists have proposed ideas like parallel universes, where changes in one timeline create alternate realities rather than altering the original one. Yet, even as science delves deeper into the mysteries of time, the concept remains elusive. Beyond the equations and theories lies a deeper, more personal question. What does time mean for us? For many, time is a relentless force that governs our lives. We measure our achievements by their passage, cherish memories of times gone by, and fear its inevitable march. It is both our greatest ally and our greatest enemy. offering moments of joy and opportunity, but also taking them away. The arrow of time, the one-way direction in which we perceive its flow, is deeply ingrained in our reality. It shapes our understanding of causality, guiding our lives with a sense of order. The past influences the present, which in turn shapes the future. This forward motion is reflected in the laws of thermodynamics, particularly the second law, which states that entropy, or disorder, always increases over time. A broken glass cannot spontaneously reassemble itself. The past is fixed and the future remains uncertain. Yet, this seemingly unbreakable rule of time's flow is not without its complexities. In the quantum realm, particles behave in ways that defy our everyday experiences, challenging our perception of a linear timeline. Experiments have shown that certain particles can exist in multiple states simultaneously, or even influence events that have already occurred, a phenomenon known as retrocausality. These findings suggest that time may not be as straightforward as it appears, adding layers of mystery to an already enigmatic concept. As we venture further into the scientific and philosophical study of time, we also encounter its portrayal in culture and media. Time travel, for instance, has been a popular theme in literature, movies, and television for decades. From H.G. Wells's The Time Machine to modern blockbusters like Interstellar, these stories capture our imaginations and challenge us to think about the possibilities and consequences of manipulating time. While these narratives often take liberties with scientific accuracy, they spark a sense of wonder and curiosity, inviting us to explore questions that may one day lead to groundbreaking discoveries. But time is not just a subject of academic study or creative inspiration. It is deeply personal. It defines our existence, from the moments that make up a single day to the years that shape our lifetime. Our memories, hopes, and dreams are all tied to time, and our understanding of it influences how we live our lives. By contemplating the nature of time, we are in essence reflecting on the nature of ourselves and our place in the universe. This journey into the heart of time will take us through its many facets, its scientific foundations, its paradoxes, its portrayal in culture, and its profound philosophical implications. We will explore the possibilities of time travel, the arrow of time's relentless direction, and the very nature of existence within its boundaries. Along the way, we will confront questions that challenge our deepest assumptions about reality and open our minds to new ways of thinking. We will uncover how time has shaped our understanding of the universe, how it continues to defy our expectations, and how its mysteries inspire us to dream. From the profound discoveries of Einstein's relativity to the tantalizing possibilities of wormholes and time travel, from the relentless march of entropy to the fleeting moments that define our lives, time is a subject that touches us all. So, as you settle in, let your curiosity guide you. Allow the questions and ideas to flow freely, like the currents of time itself. Together, we will explore the depths of this elusive dimension, seeking not just to understand time, but to appreciate its beauty, its complexity, and its profound connection to our existence. Welcome to the journey into the heart of time. Time and space, the scientific perspective. In the grand theater of the universe, time and space are not separate players, but intertwined threads of a singular tapestry. The universe is a grand stage, an intricate dance where time and space are not merely backdrops, but active participants. The story of how we came to understand this interconnection is a journey through centuries of exploration, imagination, and discovery. It reveals not only the vastness of the cosmos, but also the intimate rules that govern its behavior. To many, time seems like a universal constant, ticking forward in a steady rhythm, while space is the infinite canvas upon which events unfold. However, modern physics tells a different tale. Time and space are not static, unchanging entities. They are dynamic, flexible, and deeply interwoven into the very fabric of reality. Time was thought to flow like a river, steady and relentless, while space stretched infinitely as a neutral void. But the 20th century shattered this classical understanding, unveiling a universe far more dynamic and intertwined than we could have imagined. Albert Einstein's revolutionary theories forever altered our understanding of time and space. His insights showed that the universe operates not in separate dimensions of time and space, but in a unified realm known as space-time. This concept reshaped the way we view everything, from the motion of celestial bodies to the experience of a single moment. As we venture into the realm of Einstein's revolutionary ideas, we find ourselves on the precipice of understanding a universe far more intricate and mysterious than we could have ever imagined. It is here, in the depths of his theories, that we uncover the nature of the very fabric that holds everything together: the fabric of space-time. This concept, once foreign and unfathomable, now becomes an essential cornerstone of our understanding. Space-time is not an immutable backdrop, but a dynamic, flexible entity, capable of bending and stretching in response to the forces of gravity. To grasp this profound idea, we turn to analogies that help us see beyond the limitations of our everyday experiences, allowing us to visualize the unseen and grasp the otherwise incomprehensible. These analogies serve as bridges, connecting the abstract to the tangible, guiding us through the complexities of a universe where the laws of nature defy our traditional expectations. Within this vast and ever-shifting tapestry of space-time, another intriguing phenomenon comes into focus: time dilation. Time, as we know it, is not a constant. Under certain conditions, it bends and stretches, behaving in ways that challenge the very essence of our understanding. As we move through the universe faster and faster, time itself distorts. The faster we travel, the more time slows down for us relative to those who remain stationary. This remarkable distortion, this alteration in the flow of time, is not confined to the realms of science fiction, but is an undeniable part of the fabric of our reality. The interplay between time, space, and gravity reveals a world where the passage of time is not the same everywhere, and where the very flow of moments can be altered by speed and mass. As we leave behind the comforting simplicity of Newton's universe, with its rigid, unchanging laws, we are drawn into a new and unfamiliar world. In this world, time no longer marches forward uniformly. Instead, it flows differently, depending on where you are and how fast you move. This is a reality that both challenges and broadens our perception, forcing us to reconsider everything we once believed to be true about time, space, and the nature of existence itself. And so, we continue our journey, moving deeper into this fascinating and complex universe, where the very fabric of reality is far more malleable than we could have ever dreamed. The next chapter of our exploration beckons, one that will further unravel the mysteries of the universe, where we encounter the profound concept that is the very foundation of this malleable reality: the fabric of space-time. The fabric of space-time. To begin to understand the fabric of space-time, we must venture into a realm where the imagination takes precedence, for the concept itself stretches far beyond the boundaries of direct visualization. Imagine, if you will, the universe as a vast, flexible sheet, smooth and expansive, like a delicate yet resilient fabric. This analogy, though inherently simplified, allows us to glimpse into a reality that would otherwise remain shrouded in mystery. On this cosmic fabric, the presence of massive objects such as stars, planets, and black holes causes the sheet to curve and bend, creating subtle depressions or dimples within its structure. These indentations shape the very paths followed by other objects that roam through the cosmos. Smaller entities, such as comets, spacecraft, and even light, move along these curves, tracing their courses along the lines followed by the mass of these larger bodies. The universe, in this analogy, becomes an intricate web where every piece of matter leaves its mark, altering the shape and flow of space-time itself. Einstein's general theory of relativity, introduced in 1915, revolutionized our understanding of gravity by revealing that what we once thought of as a force pulling objects toward one another is in fact the result of the curvature of space-time itself. Rather than being drawn toward objects like planets or stars by some invisible force, objects in motion are simply following the natural bends and folds of this fabric. This breakthrough shifted our understanding from the old Newtonian view, which imagined gravity as a distant, invisible pull, to a more elegant and profound conception, where space and time are deeply intertwined with the very nature of mass. This revelation was nothing short of transformative, providing a clearer, more unified view of the universe in motion. To help solidify this idea, picture a heavy ball placed in the center of a trampoline, its weight causing the fabric to sag and form a visible depression. Now, imagine rolling a marble across the surface of the trampoline. As the marble moves, it spirals inward toward the ball, not because the ball is pulling it, but because the curved surface of the trampoline guides the marble along its path. This simple analogy mirrors the way planets orbit stars and how light itself bends as it passes near massive objects, such as black holes. The fabric of space-time, like the trampoline, guides objects on their journey, shaping their paths as they move through the universe. But Einstein's insights did not stop there. His theories went even deeper, unveiling the profound interconnectedness between space and time. In this new understanding, space and time are not separate entities, but form a single, inseparable continuum, a unified stage where one cannot exist without the other. The curvature of space-time is not confined to the three dimensions of space alone. It also stretches time, creating a profound connection between the two. The presence of mass warps both space and time in a delicate dance where one affects the other in ways that are subtle yet powerful. For example, in regions of strong gravity, time itself slows down. Clocks tick more slowly the closer they are to massive objects, a phenomenon known as gravitational time dilation. This effect, although imperceptible in our everyday lives, becomes significant near the most massive objects in the universe, such as black holes or neutron stars. This union of space and time creates a universe that is not static or unchanging. Instead, it is a dynamic, living entity, where the movements of stars, galaxies, and even ourselves send ripples through the fabric of space-time, subtly reshaping the cosmos in ways both visible and hidden. The very act of moving through the universe, whether it's the orbit of a distant planet or the quiet movement of light, causes the fabric to shift, creating a flow of events that stretches out across both space and time. As we pause to reflect on this intricate and elegant model of reality, it's humbling to consider how much we have yet to understand. Though we have mapped some of the pathways and contours of the fabric of space-time, vast portions of its depths remain unexplored, holding mysteries that continue to challenge, inspire, and fuel the curiosity of physicists around the world. Each new discovery, each breakthrough in understanding, brings us one step closer to unraveling the profound secrets of the universe. And yet, as we venture further, we are reminded of the beauty and complexity of a cosmos that continues to surprise, offering endless opportunities for exploration and wonder. Time dilation and relativity experiments. One of the most mind-bending implications of Einstein's theories is time dilation, the idea that time does not pass at the same rate for everyone, everywhere. While this may sound like science fiction, it has been proven through rigorous experiments and is a fundamental aspect of our universe. Time dilation occurs in two key scenarios: when an object moves at speeds close to the speed of light, special relativity, or when it is in the presence of strong gravitational fields, general relativity. In both cases, time slows relative to an observer in a different frame of reference. A famous demonstration of time dilation is the half-plane Keating experiment, conducted in 1971. Scientists placed highly accurate atomic clocks on airplanes and flew them around the world, comparing their readings with identical clocks left on the ground. The results showed that the clocks on the planes experienced time differently, running slower due to their motion relative to the Earth and their position in the weaker gravitational field of the atmosphere. Another striking confirmation comes from the Large Hadron Collider, LHC, where subatomic particles are accelerated to speeds approaching the speed of light. Particles like muons, which decay rapidly when at rest, live significantly longer when moving at such high speeds. This phenomenon occurs because time slows down for the fast-moving particles, aligning perfectly with Einstein's predictions. Gravitational time dilation, on the other hand, is observed in systems closer to home. For instance, the Global Positioning System, GP, relies on satellites that orbit Earth in weaker gravitational fields than those experienced on the planet's surface. The clocks on these satellites tick faster than those on the ground, and engineers must account for this difference to ensure the system's accuracy. Without these relativistic corrections, GPS devices would become hopelessly inaccurate within hours. These experiments and observations underscore the dynamic nature of time, challenging the intuitive idea of a universal now. For astronauts aboard the International Space Station, time passes slightly more slowly than for people on Earth, due to their velocity and distance from the planet's gravitational field. Over time, this difference accumulates, making the clocks run fractionally behind those of their terrestrial counterparts. The implications of time dilation stretch far beyond scientific curiosity. They form the foundation for our understanding of the universe's extreme environments, such as the event horizons of black holes, where time slows to an almost imperceptible crawl. They also fuel our dreams of interstellar travel, where journeys at near light speed could lead to scenarios where astronauts age far less than their friends and families back on Earth. Time dilation reminds us that time is not an absolute, unyielding force, but a flexible dimension, shaped by the cosmos's most fundamental rules. It invites us to view the universe not as a static collection of objects, but as a dynamic interplay of forces, fields, and phenomena. A perspective as awe-inspiring as it is humbling. Time travel, theory, and paradoxes. Time travel has fascinated humanity for generations, weaving together the threads of imagination and scientific inquiry. The possibility of traveling through time, either to the past or the future, raises profound questions about the structure of the universe, the nature of time itself, and the consequences of changing the course of history. What would happen if we could revisit the past or glimpse into the future? What paradoxes would arise And how would our understanding of causality and reality be reshaped? In this section, we explore the scientific theories behind time travel, the paradoxes they create, and the enduring fascination that time travel continues to inspire in popular culture. Theoretical mechanisms for time travel. The idea of time travel has its roots in the fabric of Einstein's general theory of relativity, which reshaped our understanding of time and space in the early 20th century. Rather than being separate entities, time and space are intricately linked within a four-dimensional continuum known as space-time. And this framework allows time to bend and warp under the influence of gravity, creating the theoretical groundwork for what might be called time travel. But what are the mechanisms that could allow time travel to become a reality, at least theoretically? Wormholes, bridges across space-time. One of the most fascinating theoretical constructs for time travel is the wormhole, a tunnel-like structure that connects two distant points in space-time. Imagine a sheet of paper where 2 points are far apart. Now, fold the paper so the 2 points meet. This fold is analogous to a wormhole, where a shortcut between two different locations in space-time is formed. First proposed by Albert Einstein and Nathan Rosen in 1935, wormholes represent a theoretical solution to Einstein's equations of general relativity. They could, in theory, serve as bridges between distant regions of space or time. If a wormhole could be stabilized, it might allow time travel. The key to this would lie in the relative passage of time at each end of the wormhole. For example, one end of the wormhole might be near a massive object like a star, where time would slow down due to the intense gravitational pull, while the other end of the wormhole might be situated far from such a massive body, where time would flow at a normal rate. A traveler could enter the wormhole at one end, experience time much slower at the other end, and potentially travel through time. However, the challenges of creating a stable wormhole are staggering. Wormholes would require exotic matter with negative energy density, something that has never been observed, but is theoretically necessary to keep the wormhole open. Without such matter, the wormhole would collapse almost instantly, preventing any possibility of passage. The idea of stabilizing a wormhole remains speculative, and no technology exists to make such phenomena possible. Closed time-like curves, loops in space-time. The concept of closed time-like curves is another intriguing mechanism that could allow for time travel. The CTCs represent paths in space-time that loop back on themselves, enabling a traveler to return to their own past. These loops could, in theory, exist near extremely rotating black holes, or Kerr black holes, which have a particular property that could enable a CTC. In the case of a Kerr black hole, the space-time around it twists in such a way that an object entering this twisted region might travel back in time. In principle, a CTC could allow an object to travel around the black hole and return to the past, creating a loop where events can repeat themselves. However, this kind of time travel would also require the same exotic conditions necessary to stabilize a wormhole, such as negative energy or an incredibly precise understanding of quantum fields. The theory behind CTCs is both fascinating and troubling. If a time traveler can return to their own past, the question arises, what happens to causality? Could a single action in the past radically change the future? Or would the universe somehow protect the timeline, preventing the traveler from affecting the past in a meaningful way? Challenges to practical time travel. While both wormholes and closed time-like curves are theoretically possible according to the equations of general relativity, there are immense practical challenges to making these phenomena real. For one, we would need technologies that are currently far beyond our reach, such as harnessing the power to create exotic matter or manipulating space-time on a macroscopic scale. Moreover, these mechanisms would require controlling intense gravitational fields and energies on a scale far greater than any human-made technology can manage today. Even if time travel could be theoretically achieved using these constructs, we are left with the question of whether the universe itself would allow such paradoxical situations to unfold. The grandfather paradox and causal loops. While time travel holds exciting potential, it also introduces the possibility of paradoxes, logical contradictions that challenge the fabric of reality itself. These paradoxes form the crux of the problems that arise when we contemplate time travel to the past. One of the most famous time travel paradoxes is the grandfather paradox, which has intrigued philosophers and scientists for generations. The grandfather paradox. The grandfather paradox explores the situation where a time traveler goes back in time and prevents their own existence. Imagine a scenario in which a person travels to the past and inadvertently prevents their grandparents from meeting. As a result, the time traveler's parents would never be born, and consequently, the time traveler would never exist. But if the time traveler never existed, how could they have traveled back in time to prevent their grandparents from meeting in the first place? This paradox highlights the logical inconsistency that arises when time travel allows changes to the past. If actions taken in the past can erase the conditions necessary for those actions, we are left with a reality that cannot make sense of itself. The grandfather paradox challenges the very concept of linear causality, where events unfold in a sequence from past to present to future. Causal loops, the feedback of time. A related but slightly different concept is the causal loop, where an event is both the cause and the effect of itself. In a causal loop, an object or information travels through time, creating a chain of events that ultimately leads to its own origination. This is a concept that arises naturally when we think of time travel, especially in scenarios involving paradoxical alterations to the past. For example, consider a time traveler who goes back to the past and tells a young inventor the blueprint for creating a time machine. The inventor uses the blueprint to create the machine, and the time traveler eventually uses it to travel back in time and tell the inventor about the blueprint. In this loop, the invention of the time machine has no clear origin. It exists because of a time traveler telling the inventor, who tells the traveler in turn. This feedback loop where cause and effect become indistinguishable is a fascinating concept in philosophy and physics. If events can feed back on themselves in this way, it raises important questions about determinism and free will, and whether actions taken in the present might be influenced by future events. Resolving the paradoxes, the Novikov self-consistency principle. One potential resolution to these paradoxes is the Novikov self-consistency principle, proposed by physicist Igor Novikov in the 1980s. This principle asserts that any time travel to the past would be consistent with the timeline, meaning that the traveler could not alter the past in such a way as to create contradictions. According to this principle, if a time traveler tried to kill their grandfather, the events surrounding the death would be such that the traveler would be prevented from accomplishing this goal. In other words, the universe protects itself from logical contradictions, ensuring that the timeline remains consistent. Branching timelines and parallel universes, quantum mechanics offers another potential solution to the paradoxes of time travel, one that doesn't involve a single, unalterable timeline. Instead, it suggests that the act of time travel could create a new, parallel timeline, effectively bypassing the grandfather paradox and allowing multiple, coexisting realities. Quantum mechanics and the many worlds interpretation. The many worlds interpretation of quantum mechanics proposes that every quantum event, every decision or random occurrence, results in the creation of a new parallel universe. In this framework, there is no single outcome to any event. Instead, every possibility splits off into its own timeline, each equally real. In the context of time travel, this interpretation suggests that if a time traveler were to change the past, they wouldn't alter the original timeline. Instead, they would create a new branch of the timeline, one where the change occurs, but does not affect the traveler's original universe. This theory provides a way to avoid paradoxes, as each decision to change the past results in a new reality, thus preserving the integrity of the original timeline. The multiverse, infinite realities. If every quantum event creates a new timeline, this implies that an infinite number of parallel universes exist, each slightly different, each unfolding according to its own version of events. The multiverse, a vast array of coexisting realities, could contain an infinite number of worlds where every possible version of reality plays out. While the multiverse remains a speculative idea, it has gained traction in both theoretical physics and popular culture. In these parallel universes, time travel could lead to the creation of entirely new realities, where the consequences of past events unfold differently. Each traveler's actions in the past would lead to the branching of new timelines, each as real as the original. Chronology, Protection, and Hawking's Conjecture. Despite the theoretical possibilities for time travel, the inherent paradoxes it introduces have led physicist Stephen Hawking to propose the Chronology Protection Conjecture, a principle that suggests the laws of physics prevent time travel to the past in order to avoid logical contradictions. The role of quantum effects. Hawking's conjecture posits that quantum fluctuations could disrupt any attempt to create a time machine or travel through time. He proposed that the universe would protect itself by preventing closed time-like curves or any mechanisms that could result in time paradoxes. This protection is thought to arise from the nature of quantum mechanics, which inherently avoids inconsistencies in the fabric of spacetime. The protection might work by preventing the formation of exotic matter needed to stabilize a wormhole, or by eliminating conditions where CTCs could occur. In this sense, the universe actively resists any attempt to tamper with the timeline, ensuring that causality is maintained. Preventing time paradoxes. Chronology protection suggests that the universe has built-in safeguards that prevent paradoxical events. These safeguards may work through quantum effects, ensuring that any time travel to the past simply isn't possible, or that any attempt to change the past will fail. For example, if a time traveler tried to stop a pivotal historical event, such as the assassination of a famous figure, like the events leading up to and surrounding the assassination might unfold in such a way that the traveler's actions would have no effect. Cultural fascination with time travel. Time travel's allure extends far beyond the realm of science. From H.G. Wells' The Time Machine to blockbuster films like Back to the Future and Doctor Who, time travel has captured the collective imagination, exploring the possibilities and dangers of manipulating time. Time travel in popular fiction. Time travel stories serve as metaphors for human desires to correct mistakes, prevent tragedies, or glimpse the future. These narratives often reflect deep psychological and societal concerns, offering insights into human nature. They also allow for the exploration of what-if scenarios, how history might have changed if key events had played out differently. The paradoxes in fiction. Time travel stories often simplify or overlook the complexities of paradoxes for the sake of narrative convenience. For example, movies like Back to the Future ignore the potential logical contradictions that might arise from changing the past. In these stories, time travel is a device to explore themes of destiny and self-determination, rather than adhering to scientific accuracy. Inspiring scientific inquiry. Though rooted in fiction, time travel also inspires scientific inquiry. The theories of relativity, wormholes, and quantum mechanics, which allow for time travel in the abstract, are grounded in real physics. Popular media help bring these ideas to a broader audience, sparking curiosity and inspiring future generations of scientists to probe the mysteries of space-time. Time travel remains a captivating and complex idea, bridging the gap between science fiction and theoretical physics. While the mechanics of time travel are still speculative, the scientific theories that suggest its possibility continue to spark fascination and challenge our understanding of the universe. Whether time travel will ever be achievable is still an open question, but it forces us to confront the deepest questions of existence, causality, and the structure of reality. The beginning of the universe, the Big Bang and beyond, the universe we know. The stars, galaxies, and all the vastness between them has a history that stretches across billions of years. But the very beginning of this history, when the universe, as we understand it, came into existence, is far more perplexing than we can fully comprehend. At its most fundamental level, the story of the universe is a story of time, space, matter, and energy coming into being from a single point, an event that forever changed the fabric of existence. This is the story of the Big Bang. The concept of the Big Bang is one of the most revolutionary ideas in the history of science, yet it remains one of the most misunderstood. For much of human history, the universe was believed to be eternal and unchanging. The idea that the universe had a beginning, a moment when everything we know sprang into existence, was inconceivable to many. But the 20th century, with the advent of modern physics and cosmology, fundamentally transformed our understanding of the universe's origins. The Big Bang theory, as it is known today, traces its roots back to the work of Edwin Hubble in the 1920s. Hubble discovered that galaxies are moving away from us in all directions, suggesting that the universe itself is expanding. This was a critical discovery because it pointed to a singular origin. It must mean they were once much closer together at some point in the distant past. At the core of the Big Bang theory lies the idea that the universe began from an extremely hot, dense state around 13.8 billion years ago. This state is often called a singularity, a point where all matter and energy are concentrated in a space of infinite density and temperature. According to Einstein's theory of general relativity, such a singularity marks the boundary where the laws of physics break down and our current understanding of time and space no longer applies. The Big Bang wasn't an explosion in space, but an explosion of space. The expansion of the universe is not occurring within pre-existing space. Space itself is stretching, and in doing so, it carries matter and energy along with it. This means that in the moments following the Big Bang, the universe was expanding at an unimaginable rate, setting the stage for everything we observe today. The first moments of the universe were governed by extreme temperatures and pressures. In the first few seconds after the Big Bang, the universe was a hot soup of elementary particles, quarks, electrons, and neutrinos, flying in every direction at nearly the speed of light. At these incredibly high temperatures, atomic structures could not exist. The universe was a vast, glowing plasma where light itself was constantly scattered by free electrons. As the universe expanded, it began to cool. and within the first few minutes, the quarks that had previously roamed free combined to form protons and neutrons. These particles began to collide and fuse, forming the first atomic nuclei in a process known as Big Bang nucleosynthesis. During these first few minutes, light elements such as hydrogen, helium, and traces of lithium were forged. For the first 3, 8, 0, 0, 0 years of the universe's existence, it remained opaque. Photons, for particles of light, could not travel freely because they were constantly scattered by free electrons. But as the universe continued to cool, electrons combined with protons and nuclei to form neutral atoms. This allowed light to travel freely, marking the beginning of the cosmic era of transparency. The first light, the cosmic microwave background (CMB) radiation, was released, and it would remain as a faint echo of the universe's infancy. Detectable to this day, the mystery of the singularity. What happened before the Big Bang remains one of the deepest mysteries in science. The term Big Bang is somewhat misleading. It implies an explosion in space, but it wasn't an explosion in space as we understand it. Instead, the Big Bang marks the birth of space and time itself. Thus, asking what happened before the Big Bang doesn't have the same meaning it would if we were discussing events within the universe, as there was no before in the traditional sense. This concept of the beginning of time itself challenges our most basic intuitions. Without a pre-existing time, there's no way to measure the before. The singularity from which the universe originated is a point in space-time where both the density and curvature become infinite, and thus our current understanding of physics ceases to function. The idea of a beginning point for time itself is not only a scientific dilemma, but also a philosophical one. If time itself began with the Big Bang, what, if anything, came before it? Cosmic inflation, the rapid expansion. One of the key features of the Big Bang theory is the concept of cosmic inflation. This idea, introduced by physicist Alan Guth in the early 1980s, suggests that in the first moments after the Big Bang, the universe underwent an exponentially rapid expansion. The inflationary epoch lasted for a tiny fraction of a second, but had profound consequences for the structure of the universe. The need for inflation, one of the challenges with the original Big Bang model, was that it did not fully explain the uniformity of the universe. Observations showed that the universe is nearly uniform in all directions, with galaxies and cosmic structures spread evenly across vast distances. However, the standard Big Bang model could not explain how regions of the universe that were not in contact with each other could have come to such similar states. Inflation solves this problem. According to the theory, the universe expanded at an unimaginable rate in the first microseconds after the Big Bang. During this brief period, the universe grew from an infinitesimally small point to the size of a melon in a fraction of a second. This rapid expansion smoothed out any irregularities, creating a nearly homogeneous universe. Inflation also explains why distant parts of the universe appear so similar, despite being far too far apart to have exchanged information. The physics of inflation. Inflationary theory proposes that the expansion was driven by a high-energy field known as the inflaton field. This field was responsible for the rapid acceleration of space-time itself, causing the universe to grow exponentially. As inflation ended, the energy from the inflaton field was converted into particles, creating the matter and radiation that make up the universe. The end of inflation marked the beginning of the more gradual expansion that we observe today. The energy released during inflation set the stage for the formation of cosmic structures, from stars and galaxies to the vast cosmic web that defines the universe's architecture. Evidence for inflation. While inflation is a compelling theory, it remains difficult to test directly. However, there is significant indirect evidence supporting it. One of the strongest pieces of evidence comes from the cosmic microwave background called pineapple bean. The CMB contains tiny fluctuations in temperature that provide a snapshot of the universe at around 3,8,000 years old. These fluctuations are the seeds of galaxies, clusters, and other cosmic structures, and inflation explains how these seeds were distributed so evenly across the universe. Scientists have also detected gravitational waves in the CMB, a phenomenon that would have been created during inflation. These ripples in spacetime provide further confirmation that the universe did indeed undergo a period of rapid expansion. The first few moments, formation of matter and energy. In the moments after the Big Bang, the universe was an incredibly hot, dense soup of particles, radiation, and energy. As it expanded and cooled, the first building blocks of matter began to form, creating the foundation for the universe's vast complexity, the formation of subatomic particles. In the first microseconds after the Big Bang, the universe consisted primarily of high-energy particles, quarks, leptons, and photons. Quarks, the fundamental building blocks of protons and neutrons, were free-floating in this primordial soup. As the universe expanded and cooled, quarks began to combine to form protons and neutrons. These particles then combined to form the nuclei of the lightest elements, hydrogen, helium, and small amounts of lithium. During the first few minutes of the universe's existence, Big Bang nucleosynthesis occurred, and the first light elements were created. Hydrogen, which would later become the most abundant element in the universe, was formed in vast quantities, alongside helium and traces of lithium. These elements would serve as the building blocks for the first stars, galaxies, and ultimately, life itself, the formation of atoms. However, it wasn't until around 3,8,000 years after the Big Bang that atoms as we know them could form. The universe had cooled enough for electrons to combine with protons and nuclei, creating neutral atoms. This process is called recombination, and it marked the transition from an opaque plasma to a transparent universe filled with neutral hydrogen atoms. At this point, the universe was bathed in light, but it was not until billions of years later, when galaxies and stars began to form, that this light would begin to reveal the grand structure of the cosmos. The cosmic microwave background echoes from the past. The cosmic microwave background, CMB radiation, is one of the most powerful pieces of evidence supporting the Big Bang theory. This faint glow, which permeates the entire universe, is a snapshot of the universe as it was about 3,8,000 years after the Big Bang. The CMB provides us with a window into the universe's infancy, revealing the conditions that existed when the cosmos first became transparent to light. What is the CMB? The CMB is the remnant heat from the Big Bang, a glow that was once in the form of high-energy photons. As the universe expanded and cooled, these photons lost energy, stretching into the microwave part of the electromagnetic spectrum. The CMB is uniform in all directions, but it also contains tiny fluctuations in temperature, which are the seeds of the future structure of the universe, galaxies, clusters, and the cosmic web. mapping the CMB. In recent decades, missions like the COBE, WMAP, and Planck satellites have mapped the CMB with incredible precision. These maps show a detailed image of the universe's first light, offering insight into the early stages of the universe and its evolution. The fluctuations in the CMB provide clues about the density of matter, the rate of expansion, and the formation of the first structures in the universe. Beyond the Big Bang, what came before and what lies ahead? The question of what came before the Big Bang is perhaps one of the greatest mysteries in modern cosmology. Since time itself began with the Big Bang, asking what happened before is almost nonsensical. Nevertheless, theories about the origins of the universe and its ultimate fate continue to evolve. The origin of time and space. The singularity from which the Big Bang emerged is a point where our understanding of space-time breaks down. According to general relativity, the density and curvature at the singularity are infinite, meaning our current laws of physics cannot describe such extreme conditions. Some theories propose that the Big Bang was not the beginning of time, but the start of a new cycle in a series of expansions and contractions, a concept known as the cyclic model. The future of the universe. What will happen to the universe in the future? Several possibilities remain under investigation. The universe is currently expanding, and observations suggest that this expansion is accelerating. The cause of this acceleration is attributed to a mysterious force known as dark energy. If dark energy continues to dominate, the universe could expand forever, leading to a heat death, where stars burn out and the universe becomes cold and dark. Alternatively, the Big Crunch is another possibility. In this scenario, the expansion of the universe slows, reverses, and eventually collapses in on itself, causing a cosmic contraction. The fate of the universe remains uncertain, but these theories reflect the profound implications of the Big Bang's legacy. The arrow of time. Why does time flow? Time is one of the most fundamental aspects of existence. We live in a world governed by the relentless flow of time, from the moment we are born until the moment we die. Yet, despite its ubiquitous presence in our lives, the true nature of time remains elusive. Why does time seem to flow in one direction, from the past to the future? What causes this arrow of time? And why is it so different from the more symmetrical nature of the laws of physics? To understand the mystery of the flow of time, we must delve into thermodynamics, the biological processes of life, and the philosophical implications of causality and perception. Thermodynamics and entropy. The arrow of time refers to the observable, unidirectional flow of time from the past toward the future. One of the most significant factors influencing the direction in which time flows is the concept of entropy, which is deeply tied to the laws of thermodynamics. To understand why time flows the way it does, we must first explore the second law of thermodynamics, one of the fundamental principles of physics, the second law of thermodynamics. The second law of thermodynamics states that the total entropy of an isolated system will always tend to increase over time. Or, in simpler terms, systems naturally evolve toward disorder. Entropy is a measure of the amount of disorder or randomness in a system. In any natural process, the entropy of a closed system increases, driving the system from a state of lower entropy, less order. This law governs everything from the simple motion of gas molecules to the workings of complex ecosystems. It's important to note that while the first law of thermodynamics deals with the conservation of energy, stating that energy cannot be created or destroyed, the second law introduces a directionality to the flow of energy. It implies that while energy can be transformed from one form to another, it cannot return to a previously ordered state without external work being done. Entropy and the arrow of time. The concept of entropy is directly tied to the arrow of time because entropy provides a direction for time to flow. In any process, the system will evolve from a state of lower entropy to a state of higher entropy. As entropy increases, the system becomes more disordered and unpredictable, and this progression gives time its unidirectional flow. If we think of time as a series of moments or events, the increase of entropy marks the progression from one moment to the next, with time always flowing forward. This understanding of entropy helps explain why we perceive time as moving in one direction, the progression toward greater disorder in isolated systems, such as a cup of hot coffee cooling down or a gas molecule spreading out to fill an empty container, aligns with our everyday experience of time passing only in one direction, toward the future. If entropy were to decrease, or if systems were able to reset to an earlier state of order, we might perceive time as reversible. But that is not the case in the universe we live in. Entropy and the universe. The second law of thermodynamics can also be applied to the universe as a whole. The heat death of the universe, a concept that stems from the second law, refers to a state in the far distant future where entropy has reached its maximum and the universe has become uniformly cold and devoid of usable energy. In this state, no work could be done and no processes would occur. It's a fate that awaits the universe as it continues to expand and cool. This concept reinforces the idea of time's one-way flow. Just as the universe began in a state of low entropy, with highly ordered energy and matter, it is now moving toward a future of maximum entropy. This future, however distant, is irreversible. The inevitable increase in entropy and the progression toward equilibrium define time's arrow. Biological and natural processes. One of the most prominent and relatable manifestations of the arrow of time is found in biological processes. From the moment of birth to the eventual decline of life, biological organisms move through life cycles marked by growth, aging, and death. The entropy at the molecular and cellular level contributes to the physical changes that organisms undergo over time, further reinforcing the unidirectional flow of time. The aging process, a biological manifestation of entropy. The aging process is a perfect example of how entropy governs life. As living organisms grow older, their cells and tissues experience a gradual buildup of damage that is often irreversible. This damage, whether it be to DNA, proteins, or other molecular structures, accumulates over time, and the organism becomes less efficient in repairing itself. The biological mechanisms that maintain the body's integrity, such as the repair of cellular damage, become less effective with age, leading to an increase in entropy within the organism. For instance, the process of oxidative stress caused by the buildup of reactive oxygen species, ROS, in the cells damages cellular structures, leading to aging and disease. The increase in molecular disorder at the cellular level is directly linked to the broader concept of entropy in thermodynamics. At the organ and system level, the effects of aging are visible in the degradation of tissues, the stiffening of joints, the decline of cognitive functions, and the loss of physical abilities. These changes occur because, over time, the systems of the body gradually lose their ability to maintain homeostasis, further increasing entropy within the body. Entropy in biological cycles. The cycle of life, death, and reproduction is another manifestation of entropy in nature. In ecosystems, the decomposition of organic matter contributes to the cycling of nutrients and the replenishment of resources for new life. When an organism dies, its body is broken down by microorganisms, and the energy within it is released back into the environment, where it is used to fuel new growth. This process of decay and regeneration reflects the continuous flow of energy and the constant increase of entropy in natural systems. However, life itself is an ongoing battle against entropy. Living organisms consume energy to create order within their cells and bodies, maintaining their structure and function. But this internal order is achieved at the cost of increasing disorder in the surrounding environment, as energy is expended and released in the form of heat. The process of life, from metabolism to reproduction, is ultimately an exercise in managing entropy, constantly using energy to maintain biological order while contributing to the broader increase in entropy within the system. The universe and biological life. At a larger scale, the entire process of life on Earth is a part of the ongoing increase in entropy in the universe. Life exists because the Earth receives energy from the Sun, which fuels biological processes, drives weather patterns, and creates conditions conducive to life. However, the energy that sustains life on Earth is ultimately dissipated into space as heat, contributing to the overall increase in entropy in the universe. The balance between life and entropy is a dynamic one, with life actively resisting disorder, but always contributing to the greater disorder of the cosmos. Causality and perception. The relationship between causality, the concept of cause and effect, and time's unidirectional flow is fundamental to our understanding of the universe. Time's arrow is not just a physical phenomenon. It is also a mental construct, shaped by our perception of events and the relationships between them. How we experience the passage of time, and how we understand the cause and effect relationships that govern our lives is deeply tied to the second law of thermodynamics and the increase of entropy, causality, and the flow of time. In classical physics, time is often treated as a passive dimension, a simple framework in which events occur in a sequence. However, the directionality of time, its flow from the past to the future, is rooted in the law of causality, which states that causes always precede effects. In a universe where entropy is constantly increasing, the sequence of events follows a logical progression. Earlier states lead to later states, and these transitions are irreversible. This concept of causality underpins the structure of the universe, from the smallest interactions between subatomic particles to the largest cosmic events. In thermodynamic terms, causality is closely tied to the idea that systems evolve from a state of lower entropy to higher entropy. As a system moves forward in time, the events within that system become less predictable, and the effects of previous actions become less predictable. Perception of time and the psychological arrow. Our perception of time is deeply linked to the arrow of time. We experience time as flowing from the past to the future, but this perception is not universal. Physicists may describe time as a fourth dimension, in the same way they describe the three spatial dimensions, and in the equations governing motion and interactions, time can flow in either direction. Yet human beings are bound by their biological processes to experience time in only one direction. This psychological arrow of time is shaped by the increasing entropy in the brain and nervous system. Just as the physical universe evolves toward higher entropy, our minds and bodies experience changes. Memories fade, physical abilities decline, and our thoughts progress linearly from one moment to the next. The sensation of time passing, of events happening in sequence, is a result of the continuous accumulation of entropy in the systems that make up our consciousness. The psychological link between time and memory. Our understanding of the flow of time is also deeply connected to our memories. Memory itself is a process that involves the organization and retrieval of information. As we experience events, Our brains store them, creating a linear record of our past. This record, however, is constantly changing as new experiences and memories are formed and the old ones fade or become distorted. The increasing disorder in our minds, the erosion of memories over time, is an internal reflection of the entropy that governs the universe. In everyday life, our experience of time's passage is shaped by our interactions with the world around us. We measure time in seconds, minutes, and hours, and our perceptions of the past, present, and future are influenced by our ongoing actions. The perception of time's flow is not just a mental phenomenon, but a biological one, grounded in the increasing entropy within our bodies and minds. Time in philosophy and popular culture, time governs our lives. It dictates everything from our waking hours to our final breath, shaping the rhythm of our existence. But for all its undeniable influence, time remains one of the most enigmatic aspects of reality. Is time a fundamental feature of the universe, or is it merely an illusion, an invention of the mind to make sense of our experiences? This section explores the philosophical ideas that challenge our understanding of time, considers how these theories might impact our daily lives, and examines the misconceptions about time that permeate popular culture. Time as an illusion. For centuries, philosophers have debated the true nature of time. Is time something real, existing independently of human perception, or is it merely a mental construct that helps us organize our experiences? In this section, we explore two dominant philosophical perspectives on time: the presentist view, which holds that only the present moment is real, and the eternalist view, which posits that all moments in time, past, present, and future, exist simultaneously. Presentism, the primacy of the present. One of the most intuitive ways to think about time is through the lens of presentism. This philosophical theory asserts that only the present moment is real. The past is gone, and the future has not yet arrived. The present is the only point where existence can be found, and the past and future are merely abstract concepts that do not have a physical reality. Presentism aligns with our everyday experience. We live in the present moment, and everything we do happens in the here and now. The past, though remembered, is no longer tangible, and the future remains uncertain. This view of time reflects our psychological experience, where the present is vivid, while the past is a fading memory, and the future is always unknown. However, presentism raises challenging questions. If only the present exists, what happens to the past and the future? How do we account for the seemingly real nature of past events, which continue to affect the present, or the anticipated future that guides our decisions? Presentism seems to conflict with the scientific understanding of time, particularly with theories of relativity, which suggests that time is a more fluid and interconnected dimension. Eternalism, all moments are real. Well, in contrast to presentism, eternalism suggests that all moments in time, past, present, and future, are equally real. According to this view, time is like a block, and all events, whether they are in the past or the future, are laid out in their entirety within this block. Eternalism treats time as a dimension similar to space. Just as all places in space exist, whether or not we are there, all moments in time exist, regardless of our awareness of them. The implications of eternalism are profound. If all moments are equally real, then the future is not just an abstract possibility. It already exists in some form, waiting to unfold. Similarly, the past does not fade into nothingness, but continues to exist in its own right. This view challenges our experience of time as a flowing river, with the present always in motion. One of the most famous arguments for eternalism comes from the theory of relativity. According to Einstein's relativity, time is not absolute. It can vary depending on the observer's frame of reference. Different observers in different locations and speeds may disagree on the simultaneity of events, meaning that what one person perceives as the present might be experienced differently by someone else. From the perspective of relativity, time is more like a four-dimensional landscape where all events, regardless of when they occur, exist together. The illusion of time in quantum mechanics. Beyond philosophy, modern physics has also cast doubt on the nature of time. In quantum mechanics, time is often treated as a parameter in equations, a coordinate in the fabric of reality. However, quantum mechanics also suggests that time may not be as fundamental as we think. Some interpretations of quantum theory, such as the block universe theory, propose that time is an illusion of human perception, a feature of consciousness that helps us make sense of our experiences. In the world of quantum physics, particles can exist in multiple states at once, seemingly existing in all possible locations and times until they are observed. This suggests that the flow of time might be a mental construct, a way our consciousness orders events, rather than an objective feature of the universe. This brings us to the concept of the now, the fleeting moment of experience we call the present. If time is an illusion, then the now is an abstraction, a cognitive illusion that allows us to perceive time as a continuous flow, even though the universe might not operate on a truly linear timeline. Time as a mental construct. Philosophers like Immanuel Kant have argued that time is not an objective feature of the universe, but rather a framework that our minds impose on our experiences. According to Kant, time is one of the a priori categories of human perception, an inherent feature of the mind that structures how we experience the world. In this view, time is not something that exists independently of us. Rather, it is a mental tool that helps us organize the events we encounter. Kant's view suggests that time is less a physical reality and more a construct of human consciousness. It allows us to understand the sequence of events, causes, and effects, but it does not exist outside of our mental frameworks. Time, then, is both a feature of human cognition and a fundamental part of how we experience reality. Impact on daily life. If time is indeed a mental construct, or if it exists as a fluid and simultaneous dimension, how would that affect our daily lives? Our understanding of time governs nearly everything we do, from how we organize our day to the way we relate to one another. In this section, we explore how our perception of time influences the way we live, think, and interact with the world. Mindfulness, experiencing the present moment. The idea that time may be an illusion has profound implications for the practice of mindfulness. Mindfulness, which involves focusing on the present moment with awareness and without judgment, seeks to transcend our habitual preoccupation with the past and future. In many mindfulness traditions, particularly in Buddhism, the practice emphasizes the transient nature of time and the importance of being fully present in the now. If time is an illusion, as some philosophers and spiritual traditions suggest, then the present moment is all we truly have. Our experiences of the past and future are often mental projections that distract us from fully engaging with our lives. Mindfulness helps us break free from this illusion by teaching us to embrace the present as it is, without the burden of past regrets or future anxieties. In the modern world, where we are constantly bombarded with distractions and the pressures of time management, mindfulness offers a way to reclaim our relationship with time. By focusing on the present moment, we can experience a deeper sense of peace and connection with ourselves and the world around us. Time and relationships. Time's passage also plays a central role in how we form and experience relationships. In romantic relationships, for instance, time spent together is often viewed as a valuable commodity. The more time two people spend together, the stronger their connection can become. Yet, if time were truly fluid, would our perceptions of relationships change? Would we value the present moment more deeply, knowing that all moments are equally real and interconnected? In families and friendships, time plays an essential role in how we create memories and build bonds. Shared experiences over time create a sense of history and belonging. If time were not linear, how would we experience these bonds? Would relationships become less tied to the passage of time and instead exist in a more timeless way? Societal structures and time. On a larger scale, our societal structures are deeply rooted in the linearity of time. Work schedules, school systems, and even political cycles are all based on the assumption that time flows in one direction. What if time could be manipulated? Could societies function differently if people were able to perceive time more fluidly, or if time itself were not such a rigid constraint? From the global economy to personal productivity, time management has become a cornerstone of modern life. The structure of our days is dictated by clocks, calendars, and deadlines. The concept of wasting time has become anathema to the productivity-driven culture of the 21st century. But what if this constant race against time were unnecessary? If time were less of a linear progression and more of a cyclical or simultaneous phenomenon, how might our societies change? Pop culture misconceptions. The way time is portrayed in popular culture, especially in movies and TV shows, often departs significantly from the scientific understanding of time and its philosophical implications. While time travel and time manipulation are popular themes, many of these portrayals introduce inaccuracies and misconceptions about how time truly works. The depiction of time travel? Perhaps the most common time theme in popular culture is time travel. Movies like Back to the Future, The Terminator, and Doctor Who all feature characters traveling through time to alter the past or visit the future. However, these portrayals often overlook the paradoxes and challenges associated with time travel, such as the grandfather paradox and the consequences of altering history. In many of these stories, time is treated as a malleable entity that can be bent, altered, or reversed without any real consequences. This portrayal is at odds with the philosophical and scientific view that time is irreversible, with events leading to increased entropy and greater disorder. The idea that time can be fixed or manipulated to suit a narrative ignores the broader implications of time's unidirectional flow and the potential consequences of altering past events. Time in fantasy and science fiction. Even in science fiction, where time manipulation is often central to the plot, time is portrayed as something that can be reversed or controlled at will. For instance, the concept of time loops, as seen in movies like Groundhog Day or Edge of Tomorrow, often suggests that characters can relive the same period of time indefinitely, making different choices and changing outcomes. While these loops make for compelling narratives, they also gloss over the implications of time as a non-perversible linear progression. The cultural adage, "time is money," is pervasive in both popular culture and real-life economics. It implies that every second is valuable and must be spent productively. However, this perspective disregards the fluidity and subjectivity of time. In film and television, characters often work against the clock, racing to accomplish tasks before time runs out. While this makes for tense drama, it misrepresents the true nature of time. which is not a currency to be spent or saved, but a dimension to be experienced. Reflective conclusion: the infinite journey of time. Time, the silent thread that runs through every moment of existence, has been the subject of wonder, exploration, and contemplation for millennia. From the ancient philosophers who pondered its nature to the groundbreaking theories of modern physicists, time remains one of the most elusive and awe-inspiring aspects of reality. Despite our greatest efforts to understand and measure it, time continues to defy our grasp, offering us not just answers, but an endless stream of questions. In this journey through the concept of time, we've explored its foundations in thermodynamics, its fleeting nature in our daily lives, its paradoxical implications in the realm of philosophy, and the often misguided portrayals in popular culture. We've asked whether time is an illusion or an unchanging constant, whether it is a river that flows in one direction or a vast ocean where all moments coexist. And as we reach the end of our exploration, we find that the mystery of time is not one to be solved, but one to be marveled at, appreciated, and reflected upon. Revisiting the awe and mystery of time. Time is more than a ticking clock. It is the pulse of the universe, the silent force that governs the very fabric of reality. From the moment of the Big Bang, when time itself began, to the eventual heat death of the universe, time has been the ever-present backdrop against which the drama of existence unfolds. But what is time, really? Is it a dimension we move through? Or is it a construct of our perception? Is time a mere illusion? A mental model we use to navigate our lives? Or is it an intrinsic feature of the cosmos? In the theories of relativity, we saw that time is not a fixed, immutable entity. It can stretch, bend, and warp in response to gravity and motion. For an astronaut near a black hole, time might move slower than it does for someone standing on Earth. This bending of time challenges our understanding of reality, pushing us to reconsider what we think we know about the world. If time can be altered, what does that mean for our experience of it? Is time truly linear? Or is it simply the way we perceive a more complex, multi-dimensional reality? This is where the awe comes in. The vastness of time is not just about its scale, its beginning at the Big Bang, its unrelenting march forward toward the distant future, but about its very nature. Time exists as both an intangible concept and a physical reality, stretching from the microscopic to the cosmic, governing the lives of atoms and galaxies alike. Time molds the universe, and at the same time allows us to exist within it, to experience moments, memories, and the fleeting sense of now. And yet, despite all our understanding, time remains elusive. It is the one thing that seems both omnipresent and intangible, always present in every moment of our lives, yet slipping away, never to be recaptured. Every moment we experience is a gift, a brief flicker in the vast expanse of time. The past has gone, the future remains unseen, and all we have is the present. Fleeting and precious, pose thought-provoking questions. Could time travel ever be real? It's a question that has captured our imaginations for centuries, and one that continues to spark heated debates in both scientific and philosophical circles. While the laws of physics, particularly Einstein's theory of relativity, suggest that time travel is possible in some form, the practical implications and paradoxes associated with it seem insurmountable. Could we ever truly travel to the past? And if we did, what would the consequences be? Would we create ripples in the fabric of reality that could alter the course of history? The concept of time travel raises fundamental questions about the nature of causality. If we were able to alter events in the past, would we risk unraveling the very fabric of the present? Could we undo the events that led to our existence? Or would the universe protect itself from paradoxes, as some theories suggest? And if we could visit the future, what would we find? A world of infinite possibilities, or a world already set in stone, governed by the laws of entropy and time's unyielding flow. But beyond the theoretical questions, time travel forces us to confront our deepest desires and fears. What would it mean for humanity if time travel were possible? Would we try to change our past mistakes, revisit our most cherished memories, or explore the unknown future? Or would we be content with the knowledge that time, in all its mystery, is the one thing that cannot be controlled or manipulated? What if, instead of trying to bend time to our will, we embraced its flow and the present moment? In a world where we are constantly chasing the next moment, the next success, or the next adventure, perhaps the true power of time lies in our ability to experience the now. What would happen if we focused not on escaping time, but on fully living in it, embracing the beauty of the fleeting present, leaving the audience in a state of calm curiosity? As we conclude this journey through the concept of time, we are left with more questions than answers, and that is the beauty of it. Time is not something that can be fully understood or controlled. It is a force that shapes the universe and our lives in ways that are both awe-inspiring and humbling. The more we learn about time, the more we realize how little we truly know about it. Perhaps the mystery of time is meant to be a source of wonder, not something to be solved. After all, it is through this very mystery that we are able to appreciate the beauty and fragility of life. Time is the thread that connects us to the past, the present, and the future. It is the backdrop against which the story of our lives unfolds, and it is both a challenge and a gift. So as you reflect on the nature of time, ask yourself, how will you spend your time? How will you experience the fleeting moments of your life? Will you rush through them, always looking ahead to the next moment? Or will you take a moment to pause and appreciate the now? Time may be fleeting, but it is also the one thing we all share. It is what connects us to the universe, to each other, and to the very essence of existence. In a world filled with distractions and demands, the true gift of time may be our ability to experience it fully, to be present in each moment, and to marvel at the wonder of it all. Time, in all its mystery and complexity, invites us to live with curiosity, to embrace the unknown, and to find peace in the constant flow of existence. As you move forward in life, carrying the knowledge and reflections on time's nature, remember that the arrow of time points us all in one direction, forward. We cannot reverse the past or control the future, but we can choose how we experience the present. Perhaps this, after all, is where time's true magic lies, not in its manipulation, but in its acceptance.